Hi, this is going to be the thermal expansion and piezoelectric addition to the flexural elasticity part of the course. So we're going to be looking at internal strain sources and how they cause moments. So the first part of this is going to be continuing on with this 2016 test number 9 here, and 2016 test number 9, the next part, we're going to be dealing with a bimetallic expansion. So we've got this strip, which is 10 centimeters long by 1 centimeter wide, 5 millimeters thick, and is made of 2 layers. Bottom layer is tungsten, and they give you the parameters of that, including the thermal expansion coefficient, and the top layer is aluminum, and we've got the parameters of that. And they tell you the aluminum is 50% of the thickness, and we're going to figure out all these parameters about it, including the Tymoshenko coefficient, flexural rigidity, linear density, all that stuff, and then calculate the curvature, radius of curvature, and bending angle that results from this temperature difference, and then the transverse tip displacement from that. So most of the work that we do here can be pretty similar to the work that we did before, except that we're going to make the parameters depend on location. So the first step for making this work is to start a new script here and then type in the parameters. And let's so we've got the length of the beam. Let's imagine that this 10 centimeters long is the length. So that's 0.1. The width is 0.01, and it tells you that we've got 5 millimeters in thickness. We're going to call that H, 0.005. Okay, now we've got parameters that depend on where we are in the beam. So 2 layers, and then we've got 50% of the thickness in each layer. Okay, cool. So let's take the elastic constant as, how are we going to do this? How about we, from the lecture notes here, we're basically going to be working out this new formula for bending where we take into account the internal thermal strain. That's sort of like the long scope of things. That's how it's going to relate to the moment. And if there's no applied moment on this, then we're going to have that's 0. And that's how we'll find out the curvature by solving this for 1 over rho. Okay. So to do that, we're going to need to know what the parameters are as functions of location. So we will take the test here and put this a little bit over to one side so we can see all these parameters on one page at once. Now we'll put those into our computer algebra system here. Okay, so E is equal to piecewise. If let's imagine that y is the thickness direction, just like before. So if y is less than 0.5 times h, then we've got E, then E is going to be equal to, got to spell piecewise correctly, E is equal to 411 E9. Otherwise, it's going to be 70 E9. So for the otherwise, we need to say a range in that. Y is greater than 0.5 times h, then 70 E9. So that's the piecewise syntax in Maple. And there we go. Is that going to be jumping down every time? It is. Oh, that's sort of obnoxious, eh? Wonder why it's doing that. Okay, there we go. So now we're going to do the same thing for the other parameters. So new is piecewise if y is less than 0.5 times h, then 0.28. Otherwise, we're going to have 0.35. I'm just wondering, did they tell us which one was on the top? So the bottom is the tungsten. Okay, good. So we're layering this up correctly, assuming that the bottom is for the low y. That would kind of make sense. All right, so continuing on there, let's just copy paste the stuff for the other, that format of the piecewise. We've got the rho, and we're going to have one for the alpha, thermal expansion coefficient. So the density is 19,250 in kilograms per cubic meter. And if you're in the aluminum layer, 2,700, then the thermal expansion coefficient is going to be 0.43 e minus 5, or I guess 4.3 e minus 6, and in the tungsten layer to 27. So sorry, this is the tungsten 4.3 e minus 6, and then the aluminum layer 27 e minus 6. Yeah, okay, so quite a lot higher for aluminum than it is for tungsten. Okay, so that's all that. We've got that put in, and now they ask us to figure out the linear density. This is the density per unit length. That would just be the density integrated over the area. So linear density would be equal to the integral of rho, and we have to go over the whole area. Now, because nothing changes with width, you can just multiply that by the width and then integrate this with respect to the y coordinate. So y is 0 to h, would be integrating over the area. Cool? Yeah. So this is, if you think about the total thickness of this, the total area of a face there, the cross-section is b times h, right? And so if we take this cross-sectional area and you were to multiply it by 2700, you would have one density. That would be if it was solid aluminum. And if you were to take this and multiply it by 19250, if it was solid tungsten, then you would have another linear density. And the actual linear density that we have is somewhere between there. So it's more balanced towards the it's really just the middle of this, right? Because we've got equal parts aluminum and equal part tungsten. So if we have 2700 plus 19250 divided by 2, then and then take this thing and multiply by the cross-sectional area, we'd have a linear density based on some sort of average density of each of these materials, yeah? Now, what if it was not 50% tungsten, 50% aluminum? Imagine if it was like 80% tungsten, 20% aluminum. What do you think is going to happen to the linear density? Well, it's going to go up. It's going to be closer to this tungsten one. Yeah? Yeah. Okay. So that's how you integrate parameters over the cross-section. You just multiply by the width if there's no change with the width. Otherwise, we could do another integral and then integrate the parameter. But either way, you integrate the parameter over y. So we could say z is 0 to b there, and we'll get exactly the same answer as we did before. Okay, cool. So that's linear density. Now to find the total mass, all you need to do is integrate the linear density over the area. So since the linear density doesn't depend on x, right? There's nothing about this beam that changes with the x, then the total mass would be equal to linear density multiplied by L. So that's that. All right. The combined axial Young's modulus. This is like the effective sort of stiffness in the x direction, and that's just the average of the stiffness over the area, right? So we take the integral of E for y is equal to 0 to h, and then we're going to divide by just integrating from 0 to h. This is the average E over the area. So it's going to be somewhere between the stiffness of the tungsten and the stiffness of the aluminum. So about 240. Actually, since we've got equal parts, it should just be a raw average. This is the stiffness that the thing would have in response to normal forces if we were going to apply any of those. The flexural rigidity, though, is going to be based on y bar. Y bar is the location of the y coordinate. So it's like the average y position weighted by the stiffness and the area. So we integrate basically y over the cross section of the beam and multiply by E all along the way. That's the same as kind of taking the average y while weighting it by area times E. Since nothing changes with the width direction, again, we can just take this thing and then integrate from y is 0 to h, and then divide by the integral of E from y is 0 to h. So we end up with the location, and where is this location relative to the center of the beam? The center of the beam is at 0.005 over 2, so at 0.0025. And we see that this y bar is closer to the bottom. Why is that? Well, that's because the tungsten's on the bottom, and it has a higher stiffness, so we've moved the neutral axis, the y bar, the location that it's actually going to bend around in response to a moment, down as a result of that. Okay, next thing from that from that information, from that location of y bar, we can figure out the flexural rigidity. So EI, really this means the flexural rigidity about the neutral axis, so about the axis it's actually going to bend. So we take EI by, we find EI by taking the integral of E times y minus y bar squared. Y is 0 to h. And there we go. So this is the stiffness against bending around that neutral axis. Now the next part asks you to figure out the Tymoshenko coefficient, and this is an optional way to calculate how things are going to bend. So if you look in the notes, then under this moments from internal strain sources, one of the first things that we did is work out, is said, we got this this Russian paper in 1925. Tymoshenko was sort of a giant of this kind of structural mechanics, statics type physics thing, and he worked out this formula for if you have a two-layered beam and they have different thermal expansion coefficients, then what kind of curvature are you going to get in response to the internal strains that they want to have only? So if one of them wants to expand to this strain and the other one wants to expand to this strain, then you can multiply that times 6 divided by h, and then multiplied by this other thing in order to figure out how it's actually going to bend. So what you do is you'd sub in the ratio of the stiffnesses and the ratio of the A's, and then you should be able to work out what the curvature of the beam will be. Okay, so then what we need for that is that N is the ratio of the stiffnesses of the top beam to the bottom beam. So we'll say N would be equal to 70 E9 over 411 E9. M is the same thing, but the ratio of the thicknesses. So M would be equal to 1. And then from that, we can figure out what this Tymoshenko coefficient is. So the test was nice enough to remind us what that is. So maybe we'll call that Timoshenko is equal to 1 plus m squared over m squared plus 1 over n times m times n, rather 1 plus n times m plus 3, whoops, don't want to be loading any multisim yet. We'll leave that till next semester. Plus 3 times 1 plus m all squared. Okay. So this should give us Timoshenko coefficient. Oh, one thing to be careful about actually is just notice that the EI is messed up. So we have to integrate this over the whole area. So you can't forget to include the B for that. For the Y bar, it doesn't matter since you're going to include it in the numerator and the denominator. So it'll cancel out. But for figuring out the flexural rigidity, it makes a difference if you include that, especially if the width is not 1, is 1/100th like it is here. Okay, so what do we do with this Timoshenko coefficient anyway? Well, it leads to a curvature after you multiply it by the difference in thermal expansions, divide by the total thickness, and then multiply by this Timoshenko coefficient. You've got the curvature that results. So let's give that a shot. Let's take alpha at the top minus alpha at the bottom. So delta epsilon would be equal to 4.3 e minus 6 minus, or actually at the top would be 27 e minus 6 minus 4.3 e minus 6. And we're going to take this and we're going to multiply by the 5 degrees that we would be getting. So that's the difference in the thermal strains that should show up in this thing. And now we take that and we multiply it by the Tymoshenko coefficient, and we multiply by 6, and we divide by h to get the curvature. So we find 0.0271. Now, another way to calculate the curvature without going through this Tymoshenko stuff, which is actually easier if you're going to go and set up the piecewise functions for these parameters, is based on the end part of the notes here. So if we say that m is equal to 0, then we can rearrange this and see that the curvature would be negative 1 over EI times just this integral. Yeah? So let's give that a shot. So that is C is negative 1 over EI times the integral of what? E times y minus y bar times the strain. And the strain would be alpha times 5. Integrating, we have to integrate that with respect to area. So we'll multiply by b, and then we'll take y from 0 to h. Let's see what we get. Yeah. So we've got exactly the same answer as we did in the other calculation, in the Timoshenko formula calculation. Now, another thing to check out is the sign convention. So besides the sign, these are exactly the same thing. So which one is right? This formula was based on C being an upward thing, yeah? So we should be, this means that the thing should actually bend down for the setup that we've got. The aluminum's on top, it expands more, so bending down is correct. So that means the Timoshenko formula was set up for a different definition of the radius of curvature than the one that we just calculated here. And if we look at it, then under the Timoshenko formula section, you know what? We actually just put in the strain backwards. So this is supposed to be based on the bottom strain minus the top strain if you want it to be bending up. So if we were to go back to our notes here and write the delta epsilon based on 4.3 minus 27, now they're both going to be in agreement perfectly. Okay. So either way, you can figure out the curvature, and then in order to get the radius of curvature, that's just 1 over that thing. So ROC, or rho usually, is equal to 1 over C, and there we go, radius of curvature, 36.8 meters. So pretty large circle, not a lot of curvature there. The bending angle that would result, so the bending angle from all of this is all for a temperature difference of 5 degrees. Bending angle is from the arc length formula, that the arc length is equal to the bending angle times the radius of curvature. So the bending angle would be the arc length divided by the radius of curvature. So phi should be equal to L divided by the ROC, and this is in radians, so 0.00271 radians. Okay, then next part, find the tip displacement. So the tip displacement, if we're going to use the small angle approximation as before, we would take the tip would be equal to the integral of C from x is 0 to L, x is 0, or x is 0 to x, and then x is 0 to x again. This is the v at any spot, right? And then if we want v tip, we'll get that by substituting x is L into v. Okay, so that's our tip displacement. Now, how do we do this in Flex? So what we'll do is actually use these piecewise things. So you can see one example of a way to do this. We're going to look at a couple of different ways to do it in Flex. Probably the simplest way to explain is you just take all the parameters that are going to depend on position, and you set them up with a piecewise statement like this. So if we're at a y that's less than half of the distance, then we've got a certain value, otherwise we've got another one. So in this particular case, we've got 411 for the tungsten, I think, and we've got 70 for aluminum. The tungsten Poisson ratio is 0.28, and the aluminum Poisson ratio is 0.35. What else are we going to need? We're going to need alpha, and we're going to need, well, actually, rho didn't get used for anything, so we're just going to put in alpha. Alpha is equal to, for tungsten, 4.3 E minus 6, and for aluminum, it was 27 E minus 6. Then we'll put in a change in temperature of 5. Now, how do we deal with the change in temperature in the thing? Well, we're going to have to just do what we did before, where we define a mechanical strain is the thermal strain plus, or rather, okay, so hold on a sec. We'll say the mechanical strain plus the thermal strain is equal to the actual strain. So if you rearrange this for mechanical strain, then you can get that the mechanical strain is the actual strain minus the thermal strain. So no difference to what we were doing before, right? So in X, EY mechanical is EY minus EYT. EZ mechanical is EZ minus EZT. Now, in fact, we don't even have a different thermal strain in the different directions. So we can say ET is equal to alpha times del T. We're dealing only with isotropic materials, so they don't have a different alpha in the different directions, and so this is a little bit simpler. And then we can put these in here. So really the stresses are based on the mechanical strains rather than just the total strains if there's a difference. No coupling to shear, so that's easy. And yeah, there we go. So this should now be accounting for the thermal strain. We need to get rid of all of the displacements from the previous version of this problem. So we'll just put this back to 0, and we'll put that other, so we fixed in the left end, that's to 0, we got rid of that. Okay, so this should be telling us what the tip displacement is for the setup right now. Let's see if it works. Oh, we're a cube. We got to redo the size, right? Okay, so let's take the size to be the dimensions for this particular problem. So we got 10 centimeters long by 1 centimeter wide and 5 millimeters thick. I guess we said that this was the thickness and that is the width. Okay, so let's see. Oh yeah, lots of deformation. We're gonna have to turn down the magnification to see how much that is, and then how much does it move in Y? It looks like we've got a displacement at the tip of 148 microns. And what was it in maple again? 136 microns. So not bad, pretty close. What could be sources of error here? The boundary conditions are slightly different in flex versus maple. So this is also true when we were just bending it. If we want to really get allow it to be a little bit more free here, then we should perhaps not restrict the width on that surface so that it can kind of expand fully all the way around in that direction too. And that should bring us probably slightly, well, in fact, that'll bring it farther away if we're not as restrict. Well, what did that do? 145, and before it was with not as much ability to expand in one direction, it's going to end up forcing the expansion to show up more in other directions. 148, yeah. So that's part of the difference. Is this set of boundary conditions, but it's not all of the difference. So the other, where could the rest of the difference be showing up? Differences in finite element method are always potentially a problem. Limited amounts of grid spacing as we move along it could be an issue. Yeah. So all in all, though, not too bad of a setup. We've ended up with something. Ooh, look at that! Increasing the grid density has really gotten us a lot closer this time to what Maple said. So that's great. Now we're within 1% after just having a better mesh density. That's maybe a plug for why you, for real analysis, would want to buy the full version of FlexPDE so that you can use a lot more grid elements and avoid some of this element spacing error. Okay, one more question, and this is going to be from the exam from 2016. This is multimorph actuator design. So this is going to be, so a multimorph actuator is something that's designed using multiple layers, and they sort of bend and deform. They change shape. So multimorph, and it's an actuator. They change shape in response to some sort of a desired signal that you're going to put in, and we're going to design it. So this is a piezoelectric unimorph, which is one layer that's piezoelectric, another layer that's a passive. It doesn't respond piezoelectrically. And the passive layer is isotropic, and we've got these parameters. The active layer is piezoelectric with these parameters. Then what we're going to do is give it overall dimensions of 1 millimeter thickness, 2 millimeter width, 1 centimeter length, and each layer is 0.5 millimeters thick. So it's some kind of a stack there. Now the first section says if the XYZ axes are aligned with the piezoelectric crystal axes, which means that what we've got here as the X component is aligned with our global XYZ axes. We've got to figure out which dimension needs to be thickness, which should be width, and which should be length for max tip displacement per applied volt and Y. So with piezoelectricity, we're going to be dealing with the same kind of a setup as we had in this Timoshenko formula in a way. It's really based on the different strain in the length direction that you have in the different layers. So for the unimorph, we're going to have nothing for the passive layer, and then what we want to do is then maximize the strain in the lengthening direction to give us the maximum amount of curvature. We also want to minimize the thickness in that direction, other things equal. The strain in the length direction is going to be through the piezoelectric effect, showing up from the coupling coefficient here multiplied by the electric field. So we multiply this by the electric field, which is in volts per meter, and that's going to cancel this out and give us the strain in the right direction. So you can see from this matrix that the electric fields that matter after we transpose this is only the X electric field, and the X electric field for this matrix gives us an X strain and a Z strain. It doesn't give a Y strain. So what this means is that we have to make either the X direction or the Z direction the length direction in our beam, right? So it's the strain in the length direction for the beam. So that has to be X or Z for us to get a curvature, because piezoelectrically this particular material only gives us strain in X and Z in response to fields. Now the field that generates those is only the X field. So we have to pick one of those to be the length direction, and we want to get the most electric field in the X direction. The way to do that for a given voltage is to put the thickness as the X direction, and that means the length has to be Z. Why do we do that? Because the electric field that shows up is the voltage divided by the thickness. So if we make the thickness it's placed across really, really small, so this 1 millimeter thing divided by 2, then when we divide the voltage that we're applying by that really small number, we're going to have a big field, which is going to lead to a big strain, yes, in the X thickness direction, but that doesn't matter, also in the Z length direction, and that's going to give us the most deformation. Okay, so yeah, so that means that we're going to need to stack the thing in Z. Then the next thing that we want to do is basically we're going to go through how we would calculate the curvature for this thing stacked in Z. So from a Maple perspective, we can do it almost the same way as we did this piezoelectricity thing. So rather than saying that the alpha that goes from the right direction is equal to this, we're going to say that the sort of piezoelectric D, maybe the piezo strain in the length direction is going to be if we're at less than half of the thickness of the material. Now it still says Y, but I guess just pretend that this is Z. Okay, if we're on the piezo part of it, then we're going to need 10 times the electric field strength. And what did they tell us here? So we're going to pick a given electric field. Oh, 100 volts. So the electric field that we're going to have is 100. So this is 10 actually pico. 10 E minus 12 times 100 volts divided by the thickness, H over 2. That's going to be the electric field. We multiply by the coupling coefficient, and that's going to give us our piezo strain. In the isotropic material, we have no piezoelectric strain. So that's the piezoelectric strain. Cool. Alpha is not actually used, so we'll comment that out so that if it does show up, we're going to be getting an error later. So that'll just be like an error checking thing. So then what we're going to do is we don't actually need the density. That shouldn't be anywhere. The Poisson, we have to put in the components for this particular material. So the isotropic material has a stiffness of 100 and a Poisson's ratio of 0.3. The piezoelectric material is a little bit more complicated, right? So this is only the stiffness if the other directions are fixed to have zero strain. But in a beam, it's probably closer to say that the other directions have zero stress. So what we need is the inverse of the S3 component, the Z1, the length, the axial elasticity in the direction we're bending. So what we'll do is we'll take that matrix and we'll find the inverse of it after typing it in here. One more. Okay, so there's C, and that looks good. So we can figure out the inverse of that. And for S, we figure out this for our compliance, and then the effective elasticity. Whoops. Ooh, what was that? What? Okay. I'll dive into this hidden thing in Maple later. Anyway, 16 over 975 would be the inverse of E. So we need 975 over 16 for the stiffness. 975 over 16. And what units would that be in? Let's see. That would have been, we took gigapascals, we inverted it. So we're in inverse gigapascals. And then we inverted it again. So it's in gigapascals. So 975 E9 over 16. Okay. And for a Poisson ratio, this is not the correct Poisson's ratio, but actually that doesn't get used anywhere in our calculation anyway. So let's not worry about it. The other dimensions that we need for this, we wanted overall 1 millimeter thickness. So that means 2 millimeters width, and how much? 1 centimeter length. Okay, so then what we'll say is we've got our effective stuff. That should all work. We don't need the total mass there. We don't need the linear density. And we've got Y bar is the same calculation. EI is the same calculation. This doesn't work for, that's not the right ratio anymore. So we'll get rid of that, get rid of the Timoshenko, get rid of the delta. That. And what we can do is rather than integrating alpha times 5, we'll just directly integrate E epsilon piezo. So that should tell us what the curvature is, radius of curvature, and the tip displacement. Cool. Okay, so tip displacement for this applied field is 0.148 microns. Right. So, let's see. First off, in Flex, because it's calculated exactly the same as a thermal expansion, with like alpha delta t for the strain in the lengthening direction, we could do the same approach that we did in Maple there, where we say we've got 975 over 975 E9 over 16, else 100. We put in the new dimensions, 0.01, 0, what's this? 0.1 and 0.02. Then we ignore the fact that the Poisson's ratio is a little bit different. We put in an alpha of the piezoelectric coupling coefficient, which is -10 E minus 12 and 0 for the isotropic. And then for delta t, we'll put in the electric field, which is 100 divided by Ly over 2. And then this is sort of ignoring the crystal asymmetry of the piezoelectrics. We should get something similar to the actual result by just dealing with it this way. So let's see. I feel like there's something else I was supposed to change, but maybe not. So how do we do? The displacement at the tip looks like it's reasonably close, right? So 0.151 microns as opposed to 0.148 microns. Not so bad. Pretty similar setup there. Now the other thing that we can do in FlexPDE is try to account kind of more directly for the differences in what's going on in this setup with the real piezoelectric crystal stuff. So this should be pretty close to the actual answer that we get in Flex if we were to account for the real crystal thing. The problem is accounting for the real crystal thing means that we have a ton of different parameters to deal with. So we don't want to be typing in all the different C components being different for this piezoelectric crystal, especially if you have something like quartz. It's even more asymmetric, right? So it's a real pain in Flex if you had to include a bunch of different if statements all the way along, right? That's not going to work. So there is a better way. And if we go into the lecture notes, you can see this FlexPDE setup here. We have ways to stack the crystal using this regions syntax and using the layers syntax. So the region syntax allows you to have different parameters with different x and y values. And the layers syntax allows you to have different parameters with different positions in Z. So this code right here shows us how we would do that. So first what we might want to do is copy out this thing just to get back a piezoelectric setup in the program. Okay, so we'll grab this, we'll go back over to FlexPDE, and then what I'm going to do is hide this isotropic stuff and go and replace this whole thing with, you see some stuff is commented out, right? It doesn't really matter for this E-field solving thing from the other matrix. What do we have here? We've got the piezoelectric strains. And I guess I didn't copy quite enough of it. So we're also going to need to know how this stuff, yeah, so there's the mechanical strain and then the stress from the strain stuff. So we'll go back in with that. Yeah, we've also got some thermal stuff in here. And are those just equal to 0? Yeah, so for now those are 0. Let's get rid of that. How's everything look here? So we've got YZ xz, xy seems all good. Accounts for the different possible mechanical strains in all the different directions. No number weirdness, hopefully. Okay. And over here, everything look okay. Seems pretty good. So then what we can do is express different parameters for different layers. So one thing that you might notice from this is we've written down these components, but we haven't actually given them any values. So that shows up for the stiffness matrix components, except for declaring that they're all symmetric otherwise. And we're not going to be using this stuff right now. It would actually show up for the density and all that if we were going to be using density anywhere. So it shows up for the stiffness matrix components and the piezoelectric components there. And the E field X is volts over the thickness of the, it's got thickness of the quartz layer. So let's just call that LZ over 2 because we're going to be really stacking in Z here. Okay. So that would be the field in the, oh wait, hold on. We need our length direction to be Z, and that means we need to stack in X, we decided. Yeah, so we're going to say over Lx over 2. The X direction is going to be the thickness direction through this thing, so we're going to swap these around. 0, 1, Y can be the width, and then Z has to be the length. Cool. So in order to do this, it's actually not the layers syntax, it's this region syntax, but so far the first part of the program is all the same. Basically what you do is for a different region, you can specify different parameters. So we'd say region 1, and you can give it a name if you like, and then you can specify parameters for it. So we'll say region 1, and we'll call this maybe the piezo part. And where does region 1 exist? It goes from, if X is supposed to be the thickness direction, starts at 0, 0, and then it's going to go up to only Lx over 2, and then to Lx over 2 Ly, and then back to 0 Ly. Great, and that's going to be the piezo region. Then we'll put in region 2 just below that. So this is going to be region 2, and this is the passive region. So you could start this at the end of the first one. So Lx over 2 and 0. Then we're going to go up to Lx, and we're going to go still with Lx over to Ly. And we're going to go from there back down to Lx over 2. Now we have to look back at what the boundaries are going to be for this. So what we'll do is figure out where's the, whoops. Okay, everything's fine. No emergencies. So the boundaries between these two different layers are equal to it's the spot where we are stacking in X. So this is this surface right here where we go from this spot to the close, which is the starting spot, Lx over 2. We're moving the Y at the Lx over 2 surface. So this is the junction. X equals Lx over 2 junction. And in this sweep, that would be this surface. So at the junction, we don't want any special force applied, perhaps. So we can put the extra load stress that's applied there to 0. And if we want to fix things on this whole thing, really we just want to fix the Z surface, yeah? So we can put those values to, those loads to 0, and then for the Z, maybe bottom surface. We'll completely fix that. So now we would be good to go, except that we never actually went and defined what those material parameters were inside. So we have to take all these things that we set the parameters to arbitrary values up above, which is the C's and the D's here, and then redefine those for each material. And where you can do this is right after you've specified the material. So we can go region 1 piezo, and then type in what all of these different values are for the piezoelectric material. So for the particular test we got, oh, not that one. This is the test we're doing. Yeah. So for this test, we've got C11 is 80 E9, 22 is 100 E9, 33 going around the diagonal is 80 E9, 12 is 40 E9, 13 is 30 E9, and then 23, 40 E9, 14 0 0 0, 24 0 0, and then 0 for 26, 34 is 0, 35 0 36 0. Okay, 44 is 50 E9, that's 0 0. 55, again 50 E9, that's 0, and 56 is 50 E9. Then for the coupling coefficients, the only ones that aren't 0 are D11 and D13. So D11 is 10 E minus 12, that's 0, and negative 10 E minus 12. The rest are 0. So we're going to put those in. Okay, so that's the piezoelectric setup. We're going to take most of this stuff and apply it for the other material as well, for this passive region. But totally 0, so no piezoelectric at all. And then for the stiffness components, now I'm kind of wishing I hadn't overwritten those earlier stiffness stiffness components, although I guess we do have this set up here. So for the passive material, we've got that for C11, C1, C22, and C33. And then 12 is that. C13 is C12, C23 is C12. And then the the other components, the top right, are all just equal to 0. So we're going to grab that from over here. And then for this one, we're going to put down that this is the shear modulus. Okay, perfect. So for the passive region, we'll just need to specify what E, nu, and G are up above. We could give different values of those if those are going to depend on where we are, but since we're only going to use them once, it actually doesn't matter if we define a separate one for each region or not. So let's say E is 100 E9, nu is 0.3, and G is equal to probably should have just typed it E over 2 times 1 plus nu. Okay, so did we do it right? No, no, we did not. So what went wrong here exactly? This has to do with overlaying the material in different regions here. So the whole material is only one layer because of the stacking that we did. You see that we don't actually see any different parts there. And that has to do with going in one direction and then going over it again in the second layer. So basically by starting off starting off here at Lx over 2 and 0, and then going up to Lx, and then over this other area, and then back down to this other spot, you'd think that this would be the syntax to draw this other rectangular prism on the X face. But we can see that the result that actually happens here, if you rotate this, is that we've got something which is, well, maybe we can see it, maybe not. It's only taking up the total size. Let's make it size 1. So the grid size doesn't work, right? But the shape in X hasn't shown us 2 different layers. It goes all the way from 0.005 to 0.01. So it actually doesn't have the other part that started at 0. That seems to have disappeared after we overwrote it with this second region there. Okay, I figured out what was wrong. So in the regions part here, in the first one, I forgot to use line to close to actually close that out. So I overwrote that somehow, and that meant that that the line was still continuing from this previous one when we started it off here. So this first shape never actually finished drawing, and it's weird that Flex didn't throw an error there. So if you get rid of this, then we have only one area like we had. But by putting it back in, now we've got the first area drawn. So part of what I guess was the hint for that is that if you zoom in, then it doesn't show up there. So it wasn't that the area got overwritten, it was that it never even happened for that first region. Anyway, now that we've got that back in, for the given setup that we have, we can look at what the displacement of the tip in the Z is the length. So we would be looking for the displacement in the X direction. That would be the vertical direction in response to this voltage and field and all that stuff that we're applying. And it looks like at the far end of the whole thing, we've got a displacement of 1.46 nanometers. And how did we do in Flex again? So it looks like Flex, we had a V tip of 0.148 micrometers rather than 1.46 nanometers, 0.148 micrometers. So they're actually, I mean, numerically, besides the factor of 100, they are they're around they have the same numbers in there. So I wonder if there's some factor of 100 floating around somewhere that that we didn't include. So the electric field that we applied was the voltage divided by Lx over 2. Okay, so this is still volts 1 as opposed to volts 100. So there we go. And now we've got our displacement by putting this voltage on the piezoelectric layer, which is this blue layer. The X-directed positive field has made it try to compress in Z, and that means the whole thing tries to bend. You can put a voltage in the other direction, and now it's going to bend the other way. And if you do this at the right frequency, you can get it to resonate back and forth, and there you have a piezoelectric unimorph.